All right, so let's start. Last time we talked about an iterative method called successive over relaxation iteration, and before that we talked about an iterative method called Gauss-Seidel iteration. So let me remind the successive over relaxation iteration. So what you have is, and so you have XR plus 1, right, is equal to I minus omega L inverse 1 minus omega times I plus U, right? Sorry, omega U right times XR right times omega C, right? So this is what we have as the successive over relaxation iteration method, right? So maybe I use K there. Okay, so in this case, right, omega is equal to 1 implies xk plus 1 is equal to I minus L inverse this is 0, right? So omega is 1, so U times xk plus I minus L inverse C. And so you can notice that when you put omega is equal to 1, you get this, right? So clearly the second one is the Gauss-Seidel iteration, right? So this is called successive over relaxation method. So let me use the notation SOR for there, right? Successive over relaxation method, and this one we call it Gauss-Seidel iteration method, right? So we define this first, and then we define this, right? And now we notice that the successive over relaxation method is more of a general case of Gauss-Seidel, or in particular we can say that the Gauss-Seidel iteration is a special case of successive over relaxation method. So the convergence conditions, right? If we divide the convergence conditions for successive over relaxation method, then by just putting omega is equal to 1, we can derive the same convergence condition for the Gauss-Seidel iteration, right? So in Jacobi iteration, in the last section, right, when we talk about Jacobi iteration, we define or we verify convergence under two circumstances, right? One is whenever the coefficient matrix has the positive definiteness in it. In addition to that, some other positive definite condition holds. So the second criteria for convergence, we see that as a diagonally dominantness of the coefficient matrix. So in both cases, for Jacobi iteration, we prove the convergence. So similarly, we are going to do the same thing here, right? So we are going to prove the convergence of these two methods, right? So basically, we will prove the convergence for the SOR, and then just putting omega is equal to 1 give you the same results for Gauss-Seidel. So we will prove the convergence of the SOR method under positive definiteness condition as well as under the strictly diagonally dominant condition on the coefficient matrices. Right? So we will prove one by one. So I am going to write convergence of SOR. So the first theorem here in the convergence of SOR is about the positive definiteness condition, right? So right, so this is the first result. I should write this as a theorem. So this is theorem. If A, we always write it as I minus L minus U, with L being strictly positive definite, strictly lower triangular, and U being strictly upper triangular. So that's an obvious thing. So I don't need to rewrite everything again. So if the omega, the parameter omega we define here is a constant between 0 and 2, then the SOR method, the sequence generated by the SOR method, converges irrespective of the initial value we choose. Right? So that is the first result. So we have to prove this. And so basically, you have to prove that the spectral radius of the matrix is the spectral radius of the inflating matrix is less than 1, right? Proof. Right, so we want to prove the spectral radius of the iterative matrix is strictly less than 1. Right, so in particular, we want to show that I minus omega L spectral radius of this matrix is strictly less than 1. Right? So that is what we want to show. Right? We have already seen a lemma, right, when we talk about the convergence of Jacobi method, right, a lemma which combines positive definiteness and the coefficient matrix, right. So the positive definiteness and the spectral radius of the matrix, the relation is being seen by a certain lemma, right. So we can use that lemma again here to prove the spectral radius condition of this matrix, right. So first we will try to, so I have to write here positive definite. Then when I say positive definite, this is Hermitian as well. So clearly this is a Hermitian positive definite matrix. So now first I am going to do is I am going to simplify this matrix. Okay, so this is my matrix I minus omega L inverse, right, times 1 minus omega I, right, plus Lu. So what I am going to do is I am going to put an extra omega L here, right? So let me show the word. First, let me do this manipulation, right, in the iterative matrix. The iterative matrix is originally I minus omega L inverse times 1 minus omega times I plus omega U. So what I do is I simplify this. I multiply by this I here. Then what I put is I put a minus omega L here. So I have to put a plus omega L here, right? So that is what I do in the next step. And then I factor out minus omega from the rest of the terms. So I have an I minus omega L minus I minus L minus U. So that is A, because you choose A as I minus L minus U. So then you multiply by inverse of I minus omega L. So this inverse of this is identity times omega minus omega times this times A. So we write down the iterative matrix of the successive over relaxation method in a more simplified form, right? So now right, so now if we can show that A, because remember A is a Hermitian positive definite matrix, right? If we can show that A minus this MSOR, the spectral radius, the iterative matrix of the SOR method, Hermitian times A times MSOR is positive definite, right? Then we can show that rho of M is less than 1, right? So clearly, right? So if we show that it is positive definite, then by the lemma we studied in one of the last classes, we can say that this one is less than 1. So now our goal is to show that this one is positive definite. So this is again lot of mechanical work, right? So we have to simplify this. So that we are going to do now. So we will first try to simplify A minus MSOR Hermitian times A times MSOR, and then we shall simplify that. And then we shall see whether that is positive definite or not. Right? So we'll start writing this down. Okay, so you substitute for MSOR here, right? Because you already have a simplified form for MSOR, so you use that and substitute it there. So when you substitute it there, you can simplify. So this is A minus I minus omega. Omega is a real number, so you don't need to worry, right? But U Hermitian I minus omega L inverse Hermitian, right, times A times this I minus omega times I minus omega L inverse. Now you simplify this multiplication. So that is A minus, let me put a big bracket, I times A times I is A. This. This. Okay, so when you multiply through, you get this, right? A minus, within the whole bracket, you multiply everything out. So you get this time, this time, this, and then this time, this time, this, and then this time, this time, this, and then this time, this time, this. So eventually you will have 4 terms in it, right? So you can simplify this. Right, so then when you simplify, you get A cancelled out, and then there is a minus become plus, and this become minus. That part you can write. So now what you are going to do is you are going to factor out I minus omega L inverse Hermitian from front, and I minus omega L inverse on the back. A. right? So when you simplify this, what you do is you first take out omega Hermitian, right? A, and then, and so when you take out, and then you what you do is you take out A times I minus omega L inverse, right? So you take out both, right? So when you take out this, sorry, this is the mistake I made, right? So this has to be U, not U. This has to be A, no? Okay, so this is a mistake I made. This is A, where I put U, that is not right. So this has to be A. So then this has to be A, and this has to be A. Right? So then this has to be A, and this has to be A, and this has to be A, and this has to be A. Right? So now we are fine. Right? So what you do is you take out this. Okay? So this has to be A. Originally I write U, but it has to be A because this is A here. So now you can factor out omega A I minus omega L inverse Hermitian, right? And then on the back you write I minus omega L inverse A. And so you pull out I minus omega L inverse A times I minus omega L inverse Hermitian from the front, and you take out I minus omega L inverse A from the back. So from this, you pull this part, so this is cancelled out, right? So that's simple, and then this become plus, right? And this become plus, and this become minus, that's obvious. Now you take out an omega out, omega out, omega out. So here there is an A, I minus omega L, A inverse is here. But you pull this part out, but at the same time you have to pull this one out, right? So what you have is I minus omega L Hermitian here. Similarly, from this you will have I minus omega L inverse. Right, not inverse, you pull out inverse, or you have I minus omega L. Right? And then from this, you pull this out, you pull this out, 1 omega out, so you have minus omega A. So that is what you have. And so when you factor out in this way, from the front you take an omega and A and I minus omega L inverse Hermitian, and from the back you factor out I minus omega L inverse times A, then you ended up with this. So now if you simplify this, you will get this. So omega A I minus omega L inverse Hermitian. There is an I plus I, so there is 2I minus omega L Hermitian minus omega L minus omega A times I minus omega L inverse A. Right. So now you can combine this, right? So you know I minus omega, right? So when you factor out L and L Hermitian, right? So you can see that, right? It is L plus L Hermitian is U, right? So let me write it down here. Right, so now this is what you have, right? So when you pull out omega, you get L plus U plus A, right? And right, so you have this, right? So when you put 2i and minus omega, you take out. So you have L Hermitian plus L plus A, but L Hermitian is upper triangular matrix U. We studied in the previous case when we talk about Jacobi, right? So but you know that A is I minus L minus U, right? Because you have A is I minus L minus U, you know that A plus L plus U is equal to I. Right? So this one is I. Because it is L plus A, U plus A, so it is I. So you have 2I minus omega I. So it's basically 2 minus omega times I. So you can put that in front. Right? So because this one is I, this becomes 2 minus omega I. So 2 minus omega is the number, so you can bring it in front. And I is identity matrix, so when you multiply, it does not change anything. So you eventually will end up with this one, right? A minus M A M Hermitian A M is actually equivalent to 2 minus omega times A times I minus omega L Hermitian times that, right? So you have to show that this one is positive definite, right? So you take an x be a non-zero vector, right? So if x is a non-zero vector, then you know x Hermitian times A minus M SOR Hermitian times A times M SOR times x is basically equal to 2 minus omega times omega times, right? So A right? So when you multiply by x on both sides, right? So here, when you multiply by x Hermitian, and when you multiply by x, so eventually you will have an x Hermitian here and x here, right? So now if you take this whole thing together, then this box thing is a Hermitian of the ellipse there. It's a Hermitian of this is equal to this. So that's why I wrote this. So this is clearly, right? Right. So if you let that vector as y, then this becomes this. Okay, so then if you take y as that vector I minus omega L inverse times AX, right? Right, so if you take I minus omega L times L inverse times AX as y, then this one is equal to 2 omega times omega Hermitian times y Hermitian times y. So this one is strictly positive whenever, right? Right, so eventually you get x Hermitian times that a minus m Hermitian am times x is equal to 2 minus omega times 2 norm of y squared. Right, so clearly you know that omega is a number between 0 and 2. So this is greater than 0. It is omega is less than 2, so this one is greater than 0. Y is a non-zero vector, so norm of y is strictly greater than 0. So eventually this is greater than 0. So clearly you know that this one is a positive definite matrix. Right, so hence by the previous lemma, we know that this one is less than 1. Spectral radius of MSOR is less than 1. Okay, so that is what we need to show, because we already proved that whenever the spectral radius of the iterative matrix is less than 1, then the sequence converges irrespective of the initial value is something we already proved. So here we don't need to rewrite it again. So it's obvious that the convergence follows from this. So here in this case, you can see that omega is a number between 0 and 2. So this result is true for the number omega, the parameter omega between 0 and 2. So clearly you know that it should be true for omega is equal to 1, right? So clearly this result leads to the convergence of the Gauss-Seidel iteration as well. So I will write this as a corollary, and I will not write the proof again because it is the same proof, but you only do with omega is equal to 1. So I will write it as a corollary. If the matrix A, which is written as I minus L minus U, is Hermitian positive definite, right? Then the Gauss-Seidel iteration converges, right? So the proof is very similar. So we are not going to do it again because it is the same proof, but only difference is you put omega is equal to 1 in the previous proof and rewrite everything again. Right, so proof is similar to the proof we just did. Right, so all you need to do is you need to make sure omega is equal to 1 throughout your work. So you have to do those little manipulations there. Other than that, there is nothing special there. Right, so in this case, you know that the Gauss seidel is also convergent because SOR is converging for omega is equal to 1. Right. So that is the first criteria we see for the convergence of the Jacobi, not Jacobi. Here we see it for Gauss seidel as well as SOR, right? Same thing we see for Jacobi as well. And then again in Jacobi we see another criteria which is the positive definiteness. So here also we will do the same criteria and try to prove the same results again. So let me write down the theorem again. And this time it is about positive definiteness. Okay, so this is the results. For any initial value x naught, the SOR method converges if the matrix A, the coefficient matrix A, which you write as I minus L minus U, is strictly diagonally dominant, right? So basically what you have to do is you have to show that the spectral radius of the matrix A is the iterative matrix is less than 1, right? So again, right? So you want to have spectral radius of MSOR to be less than 1, right? So that is what you want to get, right? So clearly, you know that we have to show it by a contradiction, right? So assume and so let us assume that an arbitrary eigenvalue lambda of the SOR method, iterative matrix of the SOR method is greater than or equal to 1, right? So that is the first result. So obviously, you know, you can write it out here, right? So right, so if X is an eigenvalue of the matrix A, then you know Ax is equal to lambda x. Here you know that X is an eigenvector associated with the eigenvalue lambda, right? For the MSOR. So MSOR times X is equal to lambda x. So what you have here is this. Right, so you multiply by I minus omega L, right? So you get I minus omega L times lambda x is equal to I 1 minus omega times I minus plus omega u times x. So I move everything to the other side, right? If I move all these to this side, what I get is it's okay, so if I move everything to the other side, I will get lambda my plus omega minus 1, right? I minus lambda times omega L minus omega u is equal to 0, right? So that means, right? So this matrix is singular, right? Right, so what is the conclusion we have is, right, the matrix lambda plus omega minus 1 times I minus lambda times omega times L, right, is minus omega u is a singular matrix, right? So now what we are going to do is we are going to use the fact that A is greater or equal to, sorry, A is strictly diagonally dominant, right? So, right, so right, so let us assume that A is written in the form I minus L minus U, right? So without loss of generality, let me assume that AII is 1, right? So let us assume that the matrix A is of the form I minus L minus U. And so in that case, you know that the diagonal terms are 1, right? And all diagonal terms are Aij's, right? So now, right? So now what we are going to do is we are going to take the sum of off diagonal terms of this matrix, right? So this lambda plus omega minus 1 times I minus lambda u and lambda omega L minus lambda u. You know that U is a strictly upper triangular matrix and L is a strictly lower triangular matrix. So there are no diagonal terms there, right? So this has no diagonal term, this has no diagonal term. Only this gives you the diagonal terms in this matrix. So if you want to take off diagonal terms that are coming from this lower triangular part and this upper triangular part. So lower triangular part, if you sum up in the ith row, right, is this. And for the ith row, the upper triangular part sum gives you that, right? So this, in a way, we can try to simplify, right? So that what we are going to do is we are going to do this. And so we are going to simplify this. This is less or equal to right. So there is an absolute value of lambda here, so you can put it in front. Omega is positive, given that it is greater than 0, so you can take it out without absolute value. Here you can take the omega out, right? But lambda is absolute value of lambda, you assume that it is greater or equal to 1, right? So you assume that omega is lambda, absolute value of lambda is greater or equal to 1. So obviously when you put an extra lambda here, this becomes larger, right? So clearly this one is less than 1. So this is less than absolute value of lambda times, right? So this is what you have here. But you know that right? So diagonal term, not absolute value, you can move without that. So the corresponding diagonal term of this matrix is actually lambda plus omega minus 1. Sum of off diagonal terms are less than this, right? So now if we show that this one is larger than this, then clearly we can show that the matrix is strictly diagonally dominant, right? So that is what we are trying to show now. Right? So this is just a simple mechanical mathematical work. So I am going to leave that as an exercise for you. Right, so this is just a simple mathematical work, right? So I want you to show that this is less or equal to lambda plus omega minus 1, right? So this is just simple calculation. Let me write down the hint here, right? Right, so here this is the hint. You try to assume that lambda is an eigenvalue, so it can be real or complex number. So just assume a general complex form a plus ib, right, which you studied in A level. Right? And then what you do is you try to show that you want to show this one is less than this. So now you take the absolute value of this quantity squared minus absolute value of this quantity squared, and then you subtract. And if you show that this is greater or equal to 0, then clearly you can show that absolute value of this is strictly less greater or equal to absolute value of this. And so this part I leave it as a homework because it is just computation. Right? By just using your A-level knowledge, you can do this computation. Right? So let me come back to what we are trying to prove. Right? Right? So eventually, if you finish this exercise, you would have ended up with this line, right? So by using what we wrote earlier, right? So we have summation of I running from 1 to I minus 1, lambda omega aij, that is the lower triangular part, right? And this is the upper triangular part, is less than, strictly less than the diagonal part. So that is clearly is the condition for the strictly diagonally dominant of the matrix. Okay, so what you ended up with here is you have the matrix, right? lambda minus plus omega minus 1 times I minus lambda omega L minus omega U is strictly diagonally dominant, right? But again, a lower level math problem which says that strictly diagonally dominant matrix is non-singular matrix, right? So if a matrix is strictly diagonally dominant, then it is non-singular. But we have this matrix as non-singular, right? Right, so here we say it is non-singular, but we have this line somewhere in our proof, right? So one of those lines contradict with the other, right? So non-singularity and this are not going to happen at the same time, right? If it is non-singular, this has to be non-zero. If this is zero, then this has to be this has to be singular. So that is clearly a contradiction. So this is a contradiction, so your assumption is wrong. What you assume is, you assume that eigenvalue lambda is greater or equal to 1. Right? Right? So what we assume is for any arbitrary eigenvalue lambda of MSO R is strictly greater or equal to 1 absolute value. But that is wrong. So that means absolute value of the lambda must be strictly less than 1 for all eigenvalues of the iterative matrix of the SOR method. If all the eigenvalues absolute value is less than 1, then clearly rho of MSOR is less than 1. If rho is less than 1, then you obviously know by the very first theorem we studied in the convergence results, right? The sequence converges for any arbitrary initial value. So this is how you verify the convergence of the MSOR method. Right? Here again, I will write the remark here. Right? So corollary. Right, so the corollary of this theorem is obviously a special case of what we write here, right? So for any coefficient matrix A with A being written as I minus L minus U is strictly diagonally dominant, then the Gauss-Seidel iteration also converges. The proof is very similar, right? Only difference is you put omega is equal to 1. So when you put omega is equal to 1, only the mechanical work changes, but other than that, nothing else changes. So it's fine, right? So you can do it in a same way, right? So that again, I leave it as an exercise for you to verify the similar type of proof for the Gauss-Seidel iteration as well. So here so far we talk about two different iterations, Gauss-Seidel and Jacobi, Gauss-Seidel and SOR, but Gauss-Seidel is a special case of SOR, and earlier we talked about the iterative method called Jacobi iterative method. So these are the iterative methods we should know in this course, which is used to solve the system of equations. Right? So in the next class, it will be next Monday. We will talk a little bit more about error analysis in this case, and then we will start a new chapter called eigenvalue decomposition method. Right? So that we will start in the next class.